Hello there, and welcome to the Quantum Slumber. I'm really glad you chose to spend a little of your night here. All day long, you move through a world that seems simple enough. Drop something, and it falls. Turn a knob, and a light comes on. A coin tossed into the air has to land as heads or tails, one clear outcome at a time. Even when life feels chaotic, the basic rules underneath feel steady, almost comforting, like an old, familiar story you already know the ending to. But tucked beneath that familiar story is a second one the universe is telling. In that deeper version, reality doesn't always settle into neat either-or answers. At the smallest scales, things can hover in a kind of in-between, as if they're quietly trying out several possibilities before committing to just one. Sometimes the world behaves as if distance isn't as final as we think it is. Sometimes the simple act of checking on something seems to help decide what happens next. Tonight, we're going to drift slowly into that hidden rulebook, the one that governs the tiny building blocks of everything around you and inside you. We won't rush through jargon or chase every equation. This isn't a test, and there's nothing you have to memorize. Think of it instead as letting your mind wander through a strange museum after hours, the doors locked to the outside world. Each exhibit a small, quiet puzzle about how reality really behaves when no one is watching. As we go, you might notice questions rising up on their own. How solid is the world, really, if so much of it is written in probabilities? Why does the universe seem to keep one set of rules for everyday life, and another for the tiny, restless pieces that make it up? And what does it mean for you, lying there, knowing that somewhere beneath your ordinary day, a very different kind of physics is always at work? You don't need to chase those questions down. You can just let them drift past, like soft thoughts that are allowed to fade as you get sleepier. Before we begin this quiet walk into the quantum world, if you find that these calm, curious explorations help you relax or unwind at the end of a long day, it really does help if you tap the like button or subscribe to the channel. It tells the algorithm that there are people who want gentle science at night, and it helps others stumble onto this same little corner. And if you feel like sharing, you can always leave a comment with where you're listening from, a city, a state, or simply up too late again. For now though, you don't have to do anything but listen. Let your attention soften just a bit, and let the noise of your day fall to the background as we ease into our first question of the night. What is quantum physics, and why does the universe seem to live by two different sets of rules? Out in the world you move through every day, things behave in a way that feels reassuring. If you nudge a glass too close to the edge of a table, it falls. If you flip a coin, it comes up heads or tails. If you step outside on a clear night, the moon hangs in the sky, whether you glance at it or not. There's a kind of quiet comfort in that. Causes lead to effects, one after another, like links in a chain. Even if life feels messy, the basic rules underneath seem steady and dependable. We call this the classical world, the realm of cars and trees, coffee cups and planets, where objects have positions, velocities, and paths that can, at least in principle, be predicted. But far beneath that familiar surface, there is another layer of reality that doesn't play by those rules. Imagine shrinking your focus down, past grains of sand, past specks of dust, to the level of atoms and the particles inside them. In this tiny domain, the universe starts to behave in ways that sound less like engineering and more like a strange bedtime story. Particles act as if they can be in many places at once. Things that should be separate seem mysteriously linked. And sometimes, just the simple act of checking on something appears to change what it is. This is the territory of quantum physics. In the classical world, you can picture a small steel ball rolling across the floor. At every moment, it has a clear location and a clear speed. If you know where it is and how fast it's moving, you can work out where it will go next. The rules are crisp. An object is either here or there, moving this fast or that fast, and measurements merely reveal what was already true. In the quantum world, that tidy picture starts to dissolve. Instead of neat, solid points following perfect trajectories, You find entities like electrons and photons that behave more like soft, spread out waves of possibility. They don't always have a single, sharply defined position. They don't always choose just one path. Until you look, they live in a hazy in-between, described not by a dot on a map, but by a kind of probability cloud, a gentle maybe smeared across space. Sometimes these quantum objects act like waves, overlapping and creating interference patterns, as if reality were made of ripples on a pond. Sometimes they arrive in tiny, indivisible chunks, as if they were little grains of energy. This dual personality, wave and particle together, is one of the core surprises waiting in this smaller world. And there's another twist. In the everyday world, measuring something feels harmless. You can check the time on a clock or look at where a car is on the road without changing what those things are doing. Measurement is passive, like opening your eyes. At the quantum scale, observing can be more like touching, the process of asking, "Where are you?" or "What state are you in?" can nudge a system into giving a definite answer, collapsing a spread out cloud of possibilities into one concrete outcome. Before the question, the particle may be described as having many potential futures. After the question, only one of them is left. So, we end up with two very different rule books for reality. One for the large and familiar, where objects follow smooth paths and properties exist whether or not we're paying attention. And one for the small and subtle, where behavior is wrapped in probability, where waves and particles blur together, and where asking a question can help decide the result. Quantum physics is our attempt to write down, as carefully as we can, the rules of that second world, the one humming quietly beneath everything you can see and touch. Its equations let us predict the odds of different outcomes with astonishing accuracy, even when the underlying picture defies our usual intuition. It wasn't always obvious that a second set of rules was needed. For a while, scientists were confident that the familiar, classical laws could handle anything the universe threw at them. Only when they began to study light and matter in more detail did tiny cracks start to appear in that confidence. Little mismatches between what the equations predicted and what the experiments showed. To understand how those first cracks opened and how the quantum story truly began, we'll slip back to a time when physics believed it was almost finished, and a soft red glow from heated objects quietly announced that something deeper was hiding underneath. Imagine, for a moment, the soft glow of something heated in the dark, a coil on an old electric stove, slowly shifting from dull red to orange, a piece of iron in a forge, moving toward a brilliant white. As it heats up, the color changes in a way our eyes recognize instantly, and for a long time, physicists thought they understood this simple, gentle light perfectly. By the late 1800s, the story of physics seemed almost complete. The motions of planets, the pull of gravity, the flow of electricity and magnetism, it all fit together in a tidy framework. There was a quiet confidence that the remaining puzzles were just details, little loose threads that would be smoothed out with a bit more careful work. One of those details was the light coming from a hot object, what we now call black body radiation. The idea was simple. Take something that absorbs all light that hits it, heat it up, and ask a straightforward question. Exactly how much energy does it radiate at each color? Classical physics had tools to answer that. Equations were written, predictions were made, and then the math misbehaved. According to the old formulas, as you looked at higher and higher frequencies, deeper into the violet and ultraviolet, the amount of energy being emitted should grow without bound. The equations calmly suggested that a warm object should be blasting out infinite energy in the ultraviolet, a glaring flood that clearly did not exist. Experiments, on the other hand, showed a smooth curve, energy rising with frequency, peaking, then falling away again. No infinities, just a gentle arch. This mismatch became known, somewhat dramatically, as the ultraviolet catastrophe. It was less a loud explosion and more a quiet embarrassment. A place where the trusted rulebook was clearly wrong, but only in a very specific corner. Most of the time, The old laws worked beautifully, but here, in the glow of a hot ember, they stumbled. Enter a German physicist named Max Planck. Planck was not trying to revolutionize anything. He was methodical, careful, even conservative in his thinking. Faced with this stubborn curve of black-body radiation, he did what many theorists do when the data refuses to line up. He adjusted the math. He asked himself what sort of formula would reproduce the shape that experiment was insisting on. To make it work, he had to introduce a strange assumption. Instead of allowing energy to flow smoothly in any amount, he imagined it could only be emitted or absorbed in discrete packets, like tiny individual coins instead of a continuous stream. Each packet size would depend on the frequency of the light. Higher frequency, larger packet. He called these packets quanta of energy. In his notes, Planck treated this step almost like a trick, a mathematical convenience. He didn't claim that nature actually handed out energy in little lumps. He simply found that if he pretended it did, the curve finally matched the experiments perfectly. The impossible infinity disappeared. The arch of the black-body spectrum fell into place with quiet precision. It's easy looking back to imagine this as a moment of thunderous insight. In reality, it felt more like a careful compromise, a slightly uncomfortable patch on a beloved theory. Planck himself later wrote that he was not entirely happy with the interpretation. He saw it as a pragmatic move to make the equations behave, not a bold claim about how the universe truly worked. And yet, in that modest adjustment, something profound had slipped in. By tying energy to specific indivisible steps, Planck had taken the first small cut into the smooth fabric of classical physics. The world that had once seemed perfectly continuous now had a faint grain to it, a hint that at deeper levels, reality might come in tiny, countable pieces. At the time, this new constant he had introduced, now called Planck's constant, was just another symbol in a line of derivations. But it would soon become one of the fundamental scales of the quantum world, a measure of how chunky action and energy are at their most basic. For the moment, though, it remained a quiet idea, sitting there in the equations like a seed. It would take another mind, looking at the behavior of light itself, to pick up Planck's strange little assumption and ask a daring question. What if these packets are not just a trick, but something real? If you've ever stood in bright sunlight and felt warmth soaking into your skin, it's easy to imagine light as a kind of gentle, continuous flow, like water from a hose, or a steady breeze brushing past your face. Turn the light up, and it feels stronger. Turn it down, and it feels softer. In the classical picture, that's exactly how light was understood. A smooth wave of energy, spreading out through space. Now, picture a simple experiment. You shine light onto a clean metal surface, a piece of zinc or potassium or some other metal in a vacuum tube. According to the old rules, if you make the light more intense, if you crank up the brightness, you're pouring more energy onto the metal. The electrons inside should feel harder and harder, kicks, until some of them are knocked free and fly out. That was the expectation, but nature didn't cooperate. In laboratory after laboratory, physicists found something oddly stubborn. If they used dim light of a high enough frequency, say deep violet or ultraviolet, electrons would pop off the metal almost immediately. But if they used a very bright light of a lower frequency, for example, a strong red beam, the metal simply sat there. No matter how long they waited, no electrons were ejected. It was as if the metal didn't care how much total light energy was arriving, only whether each individual piece of light carried enough punch. If the color was below a certain threshold, nothing happened. Above that threshold, even a faint beam could start kicking electrons loose. This became known as the photoelectric effect. And it was another place where the classical story quietly cracked. If light were just a wave spreading energy smoothly across the surface, increasing the brightness should eventually give each electron enough energy to escape. But the experiment said otherwise. There was a sharp cutoff. Below a certain frequency, no emission at all. Above it, electrons flew out with energies that increased with the color of the light, not its intensity. It took Albert Einstein to take Max Planck's shy idea about energy packets and push it into a bolder form. Planck had introduced quanta as a mathematical device to fix the black-body curve. Einstein suggested something more daring. What if light itself is made of individual packets of energy? Not just as a trick in the equations, but as an actual description of how light behaves. He proposed that each of these packets, later called photons, carries an amount of energy directly proportional to its frequency. Higher frequency, higher energy per photon. When light hits the metal, you can think of it not as a smooth bath, but as a rain of tiny energetic stones. Each electron in the metal feels individual hits from these photons. If a photon doesn't have enough energy, it doesn't matter how many of them arrive. Each one still falls short of the energy needed to knock an electron free. In this picture, the threshold frequency makes perfect sense. Below that frequency, every photon is too weak to liberate an electron. Above it, even a single photon can do the job. Turning up the brightness doesn't change how strong each photon is. It just increases how many arrive per second. So, a brighter beam above the threshold doesn't make electrons possible. It just sends more of them out, like increasing the number of coins in a steady shower, not the value of each coin. Einstein's explanation rescued the photoelectric effect from paradox and turned Planck's uneasy assumption into something physical. Light, which had been treated for a century as a spreading wave, now revealed a second personality. It sometimes behaves like a shower of particles. Of course, experiments still showed light interfering and diffracting like a wave in many situations. There was no way to throw that picture away. Instead, physicists were left with a dual description that felt more like poetry than machinery. Light travels as a wave, yet is exchanged in discrete packets. It is both spread out and quantized, depending on how you ask your question. In that quiet shift of view, the universe gave up another piece of its classical mask. If light itself could blur the boundary between wave and particle, it was natural to wonder what might happen if we turned the same kind of scrutiny onto matter, onto electrons, atoms, and the building blocks of everything solid. One of the strangest clues that the universe gives us about its true nature comes from an experiment so simple you can almost picture it on a tabletop. Start with something gentle, water and a barrier. Imagine a long tank filled with still water, and in the middle of the tank, you place a thin wall with two narrow openings cut into it, side by side. On one side of the wall, you disturb the water with a steady, rhythmic motion, like tapping the surface with your finger over and over again. Waves roll outward, reach the barrier, and squeeze through the two slits. On the far side of that wall, something beautiful happens. The waves coming through each opening spread out and overlap. Where the peaks of one wave meet the peaks of the other, they add together, forming taller crests. Where a peak meets a trough, they cancel, leaving calmer spots. If you sprinkle a little dye, or watch the reflections carefully, you see a series of bright and dark bands, an interference pattern, a kind of watery fingerprint of the two-slit setup. That's what waves do. They pass through both openings at once, and their overlapping ripples write a striped pattern on the world. Now change the picture. Instead of water and waves, imagine standing in front of a wall with two narrow windows, holding a bucket of tiny marbles, or BB pellets. You throw them one by one toward the wall. Each marble either goes through the left opening or the right opening, then hits the far wall behind. After you've thrown a lot of marbles, you walk around to look. You don't see stripes. You see two clusters, one patch of impacts lined up behind the left slit, and one behind the right. Particles, unlike waves, don't spread out and overlap in the same way. Each one chooses a path and leaves a dot. So, we have two clear pictures in our minds. Waves go through both openings, interfere, create a pattern of alternating bands. Particles go through either one opening or the other, form two piles. Now we turn to the quantum world, and things stop fitting so neatly. Physicists built a version of this setup for light and for electrons, the tiny charged particles inside atoms. The apparatus is conceptually simple. a source that sends particles toward a barrier with two closely spaced openings, and a screen behind to record where each one lands. First, you let a lot of particles fly. If they behave just like bullets, you'd expect two bright regions on the screen, corresponding to the two slits. If they behave like waves, you'd expect an interference pattern, a series of bright and dark stripes. What you actually get when both slits are open and nothing is watching which route the particles take looks like the wave answer. A banded pattern appears, as if the particles collectively know about both slits and interfere with themselves. That's already odd, but you might shrug and say, well, maybe the particles are bumping into each other on the way through. Maybe this is a complicated many-particle effect. So, experimenters tried something more extreme. Instead of sending a stream, they turned the intensity way down and emitted one electron at a time. A single particle leaves the source, heads for the barrier, passes through, and hits the screen. Then everything resets. Then another electron goes, then another. On the screen at first, you only see isolated dots, appearing one by one, scattered here and there. Each electron lands at a specific point, like a tiny star blinking into existence. There is no stripe pattern yet, just lonely marks on a blank canvas. But if you're patient, if you let this continue for minutes and hours, those dots begin to accumulate. Slowly, grain by grain, a familiar image emerges. The random-looking points thicken in some regions and thin out in others, until you realize that the electrons have built up the same interference pattern you saw with waves. Each individual electron arrives as a single hit, a localized click. Yet the overall distribution of many such clicks traces out the bands of a wave. It's as if each particle takes every possible route at once, in some ghostly way, and interferes with itself. And only when it strikes the screen does it suddenly choose one specific place to appear. That picture gets even more unsettling when you try to ask a very natural question. Which slit did the particle actually go through? To find out, you can add tiny detectors at the openings, devices sensitive enough to register whether an electron or photon passes through the left slit or the right slit. You don't change the barrier or the slits themselves. You just arrange to keep track of the path. Now, you run the experiment again. Particles are sent one by one. The detectors quietly record which slit each one uses, and the screen faithfully notes where they land. When you come back to look at the accumulated pattern, the wave-like stripes have vanished. Instead, you see two broad lumps, one behind each slit, just like the simple marble picture. By trying to learn the path, you seem to have stripped away the interference. The system no longer behaves as if each particle is exploring multiple routes. It acts like a classical particle again. Nothing else about the setup changed. The slits are the same, the source is the same, the distance is the same. The only difference is that, in one case, no information was being gathered about which path was taken, and in the other, there was. This is the heart of what makes the double-slit experiment feel like a quiet dream rather than a mechanical test. The outcome depends not only on the physical arrangement of barriers and detectors, but also on whether the world is allowed to remain in ignorance about the path, or whether that information is available, even if no human ever reads it. At this scale, it's hard to cling to the idea that the particle was simply really going through one slit all along, in the ordinary sense. The mathematics that describes these experiments treats the possibilities as a kind of spread-out wave, a smear of probability that only sharpens into a single result when a measurement is made. So, we're left with a picture that doesn't fit smoothly into everyday language. Objects that can behave like waves or particles. Patterns that appear when no one keeps track of the route, and patterns that vanish when the path is, in principle, knowable. It begins to sound less like a solid, clockwork universe, and more like a story where questions and answers are deeply entangled. At the quantum level, reality seems to drift in a superposition of options, and only when we press it with a specific which way does it settle on one. To capture this strange in-between, this world where particles act like ripples of possibility, physicists needed more than pictures of waves and bullets. They needed a new kind of description, one that could hold all those maybes at once and tell us how they evolved before any measurement is made. After the double-slit experiment, it was clear that the old pictures of little balls and simple waves weren't enough anymore. Somehow, a single electron could behave as if it were spread out, feeling both openings at once, and yet always arrive as one tiny, sharp dot on the screen. Physicists needed more than a metaphor. They needed a way to describe that strange in-between, not just talk around it. This is where Erwin Schrödinger enters the story. Schrödinger was looking for an equation that would do for quantum systems what Newton's laws did for planets and projectiles. Something that would take the state of a system now and tell you how it changes with time. But instead of tracking solid particles with definite positions and velocities, he aimed at something softer, a kind of mathematical wave that could encode all those ghostly possibilities at once. He introduced an object called the wave function, usually written as the Greek letter BSI. You can think of this wave function as a quiet, underlying rhythm that runs through the quantum world, a complex wave spread out over space, whose shape and intensity at each point carry information about where a particle could be found and what it might be doing. To give it a more tangible image, imagine an atom, not as tiny planets orbiting a miniature sun, but as a small, positively charged nucleus with an electron cloud wrapped around it. In older textbook drawings, that cloud is shaded darker where the electron is more likely to be found, and lighter where it's less likely. The electron isn't literally smeared out like fog, but the cloud is a visual hint of the underlying wave function, a probability landscape showing where detection is most and least probable. Schrödinger's equation is the rule that tells this wave function how to evolve. If you know psi at one moment, his equation lets you compute how it will gently change in the next moment and the next, like watching ripples move across the surface of a pond. There's no need to picture a particle choosing a path in the classical sense. Instead, reality at that level is encoded in a spread-out pattern of potential outcomes. From this wave function, you can recover the familiar idea of probability. If you square its magnitude at some location, you get the likelihood of finding the particle there if you perform a measurement. In that sense, the wave function is not a map of where the particle is right now, as if it were secretly hiding in one of the possible spots. It's a map of where it is allowed to show up when you look, and with what odds. It's a subtle shift. In classical physics, you might say, the object is here, we just don't know it yet. In the quantum picture, before a measurement, here and there live together inside the wave function as weighted options, coexisting in a kind of mathematical harmony. Only when you perform a measurement does the system deliver a single, definite outcome. What that collapse really means is still a matter of interpretation. Some views treat it as a fundamental step, the moment the hazy wave of possibilities snaps into one result. Others see it as more of an update in our knowledge, not something the universe itself does. But all of those perspectives, even when they disagree about philosophy, rely on Schrödinger's wave function as the central object that evolves smoothly between measurements. If you like analogies, you could think of the wave function as the score of a piece of music, and each measurement as one particular performance. The score contains many potential interpretations, many ways the notes could be played: faster, slower, softer, louder. The wave function holds all the potential outcomes in a single structured pattern. When you actually listen, you get one concrete version, one line traced through all those possibilities. This way of thinking has been extraordinarily successful. It predicts the energy levels of atoms, the shapes of chemical bonds, the behavior of electrons in solids, and the spectra of light emitted by stars. Again and again, the wave function's soft, abstract maybe has translated into experiments that match with almost eerie precision. But there's a trade-off built into this description. The more faithfully we try to pin down certain aspects of a quantum system, the less sharply other aspects can be defined. Once you accept that particles are guided by a spread-out wave of possibility rather than a single, crisp trajectory, it becomes natural, and perhaps unavoidable, that there are limits on how precisely we can talk about the details of their motion. Even before anyone wrote it down as an equation, the wave function carried a quiet hint that our usual idea of precision might be in trouble. If reality at the smallest scales is expressed as a soft distribution of possibilities rather than a single, sharp path, then there is a natural question hiding underneath. How sharply can we ever hope to draw that picture? In everyday life, we tend to believe that, in principle, everything could be known if our tools were good enough. If you track a car on a highway with GPS and radar, you might say, with a better receiver, I could know exactly where it is and exactly how fast it's going. The same with an airplane or a baseball or a storm cloud drifting across the weather map. Any fuzziness feels like a temporary annoyance, something that could be polished away with more careful instruments. Werner Heisenberg discovered that, in the quantum world, that hope runs into a hard limit. Heisenberg's uncertainty principle doesn't say that we are clumsy, or that we simply need better microscopes. It says that certain pairs of properties, like a particle's exact position and its exact momentum, are tied together in such a way that making one of them clearer necessarily makes the other one blurrier. It's not a technological problem. It's built into the wave-like nature of quantum objects. A familiar analogy comes from waves themselves. If you pluck a guitar string and it vibrates in a nice, smooth, extended pattern, you can talk about its frequency very precisely. The pitch is clear and steady. But if you want to confine that vibration to a very short region in time, just a tiny tap instead of a ringing tone, the frequency content spreads out. You no longer have a single clean note, you have a mixture. Pinning something down in one domain makes it spill out in another. For quantum particles, the wave function plays the role of that vibration. If you squeeze it so that it's very sharply localized in space, so the particle is almost certainly in a very small region, the spread in its possible momenta must grow. The particle's where becomes clear, but its how fast and in which direction becomes correspondingly uncertain. If you shape the wave function so that the momentum is very well defined, the particle's position spreads out instead, like a mist. Heisenberg's principle puts this trade-off into exact mathematical form. But for our sleepy purposes, it's enough to hold on to the image. There is a structured blur at the heart of quantum behavior. It's not random sloppiness. It's more like the soft edge of a shadow, or the way a photograph taken with a long exposure smooths out the motion of a waterfall. There is shape and order and pattern, just not the kind of crisp, pin-sharp detail we might wish for. This also means that the old idea of a particle secretly carrying around perfect hidden values for everything is hard to maintain. The uncertainty isn't simply in our heads. It's in the way the world is organized at that scale. Asking for an electron's exact position and exact momentum at the same moment is like asking for a perfectly sharp snapshot and a perfectly pure tone from the same musical note at the same time. The underlying wave can't grant both wishes at once. For many people, this built-in vagueness feels unsettling. We like to imagine the universe as a clockwork that could, at least in theory, be described down to the last gear tooth. Quantum mechanics suggests something gentler and stranger, that nature keeps certain details soft on purpose, and that this softness is not a bug, but a feature. It's part of what allows quantum systems to spread out, interfere, and explore more than one possibility at a time. Inside that disciplined fuzziness, new kinds of states become possible. States that aren't simply here or there, this way or that way, but a calm mixture of several options at once. From the outside, it can feel like trying to call a coin toss while the coin is still spinning in the air. Neither clearly heads nor clearly tails, yet described by a wave that silently contains both outcomes. In that soft, hazy landscape opened up by uncertainty, one idea sits right at the center of the quantum story. The idea that a single system can calmly hold more than one possibility at once. Not as a trick of language, and not as our ignorance, but as the actual way the state of the system is described. In the world you move through every day, a coin lying on your kitchen table is either heads or tails. Even when you flip it into the air, you might say, well, I just don't know yet. But you still imagine that at every instant, it has some definite orientation. There is a hidden answer waiting to be revealed when your hand closes around it. A quantum coin doesn't quite behave like that. Instead of secretly choosing heads or tails and just refusing to tell you, it exists in a blended condition that includes both outcomes at once. Mathematically, its state is written as a combination, a weighted mixture of heads and tails. Those weights tell you the odds of getting each result, but until you actually perform a measurement, the system is not quietly one or the other. It is genuinely in a superposed state. Superposition is the name physicists give to this kind of both-at-once behavior. Because the quantum description is wave-like, you can combine states the way you combine waves on a pond. Two ripples can stack to form a bigger crest, or cancel to make a calm patch of water. Similarly, a particle's state can be a gentle sum of several possibilities, with some reinforced, some muted, all coexisting in a single, smooth description. When you finally measure the quantum coin, when you ask nature for a yes or no answer, that quiet mixture does something abrupt. The wave that once described several outcomes shrinks down to match the single result you observe. We call that collapse. Though no one sees anything physically crumple, it's more like a story that had many possible endings suddenly committing to one version as soon as you turn the last page. This can be an unsettling idea, but there is also something oddly peaceful about it. Rather than insisting that reality is always sharp and decided, quantum mechanics allows systems to linger in a space of options, to explore a range of futures in parallel, and only narrow down when an interaction forces the issue. The universe, on this view, is not racing to pin everything down at every instant. It lets certain questions remain softly open. Superposition isn't just a philosophical curiosity. It's the ingredient behind one of the most talked about technologies in modern physics: quantum computing. In a classical computer, each bit is either 0 or 1, like tiny switches snapped firmly up or down. A quantum bit, or qubit, can be in a superposition of 0 and 1 at the same time. That doesn't mean it's flickering back and forth faster than you can see. It means its state is a smooth combination of those two possibilities, with certain probabilities attached. When many qubits are allowed to share these blended states and interfere like overlapping waves, a quantum computer can, in principle, explore a vast landscape of configurations in a way that ordinary machines cannot. For our sleepy purposes, you don't need to follow the engineering details. It's enough to picture a row of tiny quantum coins, each not yet committed to heads or tails, their combined waves spreading out over an enormous range of patterns. A clever algorithm is like a choreographed dance of those waves, nudging some patterns to brighten and others to fade, so that when you finally look, the answer you care about is more likely to appear. What makes all of this work is the same gentle rule. Before a measurement, a quantum system isn't required to choose. It can rest in a superposed state, describing several outcomes at once, each with its own quiet weight in the overall wave. And as strange as that sounds, the story becomes even more intriguing when this kind of shared in-between condition doesn't just apply to a single coin or a single particle, but to two systems at once, linked together in a way that keeps their fates softly intertwined. By now, the idea of a single quantum object resting in more than one possibility at once is already strange enough. But the story becomes even more uncanny when that in-between quality doesn't just belong to one particle, but to a pair linked so deeply that you can't describe one without talking about the other. In everyday life, the closest thing we have is a simple bit of common sense. Imagine you have a pair of gloves. You slip one into a box marked A, the other into a box marked B. You seal them up, send one box across town, and keep the other on your kitchen table. You might forget which is which, but you know that if you open your box and find a left-hand glove, the other must be a right-hand glove. The moment you look, you learn something about the distant box. Nothing spooky is happening in that scene. The gloves had their identities from the start. The correlation lives in your lack of information, not in any mysterious bond between the boxes. That's how classical physics likes its connections. Predetermined, tidy, and quietly waiting for you to uncover them. Quantum entanglement does not behave so politely. When two particles are prepared in a special way, created together, interacting briefly, then allowed to fly apart, their shared state can no longer be separated into, this one is like this, that one is like that. Instead, there is a single combined wave function that describes them as one system, even when they are far away. The possibilities for their measurements are woven together in that joint description. You can still choose to measure a property, such as a kind of internal spin on each particle. And when you do, you will find correlations that look a little like the glove story. If you find spin up here, you'll find spin down there, or vice versa. But the crucial difference is that before both measurements are made, the theory does not treat each particle as secretly carrying a definite answer. The pair is held in a shared superposition of outcomes, and the specific combination only settles when observations take place. This bothered Einstein a great deal. With two colleagues, Podolsky and Rosen, he tried to show that something had to be missing from the quantum picture. If a choice made in one lab could instantly influence what was seen in another, no matter how far away, that felt like a violation of the quiet, local way he believed the universe should behave. He famously called it spooky action at a distance, and suggested that there must be hidden variables, invisible instructions, tucked inside each particle from the beginning, restoring a more comfortable picture of reality. For a time, that idea sounded reasonable. Perhaps quantum mechanics was just incomplete, a clever but unfinished sketch of a deeper theory. Then, in the 1960s, the physicist John Bell found a way to turn this philosophical argument into a testable question. He showed that any theory built on local hidden variables would have to obey certain mathematical limits on how strong those correlations could be. Those limits are called Bell inequalities. When experimenters finally carried out careful tests, first in early, imperfect setups, and later in exquisitely controlled ones, the results leaned in one direction, again and again. The observed correlations between entangled particles were too strong to fit any local, hidden variable story. Nature, it seemed, did not want to be explained by simple, the gloves were labeled from the start logic. At the same time, entanglement does not allow messages to be sent faster than light. Each measurement outcome, taken by itself, is still random. It is only when the results from both sides are brought together and compared that the pattern of correlations appears. So, causality in the everyday sense of signals traveling from one place to another remains safe. What is challenged is our comfortable picture of separate objects carrying independent properties, untouched by distant choices. For a sleepy mind, the exact technicalities aren't important. What matters is the mood of the discovery. That reality, at this level, may be less like a scattered collection of isolated pieces and more like a single, extended pattern with parts that remain subtly coordinated no matter how far they drift apart. Two particles that once interacted can go their separate ways and still behave as if they share a quiet understanding. It's hard not to feel a faint echo of that in human life, in friendships that endure across long distances, in the way a single decision in one place can ripple unexpectedly into another. Physicists are careful not to stretch the metaphor too far, but the emotional resonance is easy to hear when you're listening at the end of a long day, eyes heavy, thoughts drifting. And if tiny particles can exist in these shared, in-between states, linked across space and waiting for a measurement to decide their fate, it raises a natural, unsettling question. What happens when that same quantum logic is applied to something bigger, something alive, something curled up in a box with its future balanced delicately on the edge of a radioactive atom's decay? Imagine for a moment that instead of tiny particles on screens in distant laboratories, the strange rules of the quantum world were allowed to spill into something much more familiar, something soft and breathing and alive. Picture an ordinary cardboard box sitting on a table in a quiet room. Inside the box, where you cannot see, there is a small vial of poison, a detector hooked up to it, and a single radioactive atom with a tiny chance of decaying in the next hour. Curled up beside this delicate machinery, there is a cat resting in the dark, unaware of the thought experiment it has been drafted into. The rules are simple. If the atom decays, the detector clicks, the mechanism shatters the vial, and the poison is released. If the atom does not decay, nothing happens, the vial stays intact, and the cat is left unharmed. From the outside, with the lid closed, you have no way of knowing which path reality has taken. The trigger could have gone off or not. The atom could have decayed or remained untouched. The cat could be breathing softly, or not breathing at all. In the language of quantum mechanics, that little atom, before it's measured, is not neatly decayed or not decayed. It is described by a superposition of both possibilities, a spread of maybes written into its wave function. Schrödinger's question was, if we take that description seriously, and if the detector and the poison and the cat are all linked to that atom, then what does the wave function say about the cat? Follow the logic through, and you arrive somewhere deeply unsettling. If the atom is both decayed and not decayed, and each branch is tied to a different fate for the cat, then the combined wave function seems to describe a cat that is both alive and dead at once. Not in a way we could ever see directly, but as a mathematical description of that closed box before anyone lifts the lid and looks inside. Schrödinger did not propose this story to claim that cats really exist in gruesome, half-alive limbo. He crafted it as a kind of protest, a way of holding up a mirror to the theory and saying, if you apply your rules to everyday objects, look at how bizarre the picture becomes. The cat is there to make us uncomfortable, to force us to face the measurement problem hiding in the background. At what point does the wave function choose a single outcome? Is it when the atom interacts with the detector, when the poison is released, when the cat's body responds? Or does nothing truly settle until a conscious observer opens the box and sees a result? Different interpretations of quantum mechanics answer that in different ways. The Copenhagen view essentially says that measurement, in a broad sense, causes the collapse from maybes to a single fact. Many worlds suggest that all outcomes continue, each in its own branching universe, with the observer simply finding themselves in one of many copies. Other ideas talk about spontaneous collapses, built into the fabric of reality, that keep large objects from staying in superpositions for long. From the outside, the equations all agree on what you will actually observe when you finally look. Either a living cat or a lifeless one, never both. The disagreement lives in the story they tell about what the world is like in between, in that quiet interval when the box is still closed and the answer has not yet been read. There is something deeply dreamlike about that sealed box sitting on the table, containing a situation that the theory refuses to describe in ordinary classical terms. It's as though the universe, at that scale, hesitates between possibilities, holding open multiple futures at once, until an interaction with the wider world presses it to commit. And even if we never plan to put real cats in such cruel setups, the underlying question doesn't go away. If quantum rules allow superpositions and strange in-between states, how far do those rules extend? How big can a system be and still behave that way? Where, if anywhere, is the line between the flicker of a microscopic event and the solid, definite world we feel around us? Those are the puzzles that linger when the story of the cat is told, and they hint at something else as well, that at the smallest scales, boundaries are not always as firm as they appear. Things that should be separate can blend. Things that should be blocked can sometimes slip through. Even walls, in the quantum sense, are not always as solid as our everyday intuition expects. On the scale of everyday life, some things feel absolutely certain. If you roll a solid rubber ball straight at a brick wall, you know what will happen. The ball might bounce, it might deform a little, but it does not seep through the bricks and reappear on the other side. There is a clear line between here and there, between this side of the barrier and that side. In the quantum world, that line softens. Instead of a tiny billiard ball, imagine an electron approaching a barrier of energy, something it doesn't have enough oomph to climb over according to classical rules. If we clung to that familiar picture, we would say, well, that's that, it can't cross, end of story. But an electron is also a wave, a spread out hum of possibility described by its wave function. And waves don't just slam into obstacles, they tend to seep, fade, and echo around them. One way to picture it is to imagine a hill made of very fine sand. A classical ball rolls up, slows, and rolls back down. But a soft, hazy cloud drifting toward that hill behaves differently. Part of the cloud piles up and retreats, yes, but a thin, ghostly wisp can leak through to the other side. In quantum mechanics, that wisp is more than a metaphor. The wave function that describes the particle actually extends into, and sometimes through, a barrier it shouldn't be able to cross. Most of the time, the particle still reflects. The odds of it appearing beyond the barrier might be tiny, but tiny is not the same as zero. Every now and then, when the probabilities line up just right, the particle simply shows up on the far side, as if it had slipped through a wall that should have been solid. This quiet trick, called quantum tunneling, isn't just a mathematical curiosity. It lies at the heart of radioactive decay, where particles escape from atomic nuclei that ought to confine them. Inside stars, tunneling helps protons get close enough together to fuse, even when electrostatic repulsion says they shouldn't. Engineers harness it in delicate electronic devices and ultra-fine microscopes that can sense individual atoms on a surface. At human scale, we never watch baseballs tunnel through stadium walls, so our intuition keeps insisting that barriers are absolute. But in the small, shimmering realm beneath that intuition, even a wall has a little give. Some fraction of what approaches it can bleed through, guided not by certainty, but by the soft mathematics of probability. And this idea that even obstacles have a faint openness to them sets the mood for an even stranger realization. That empty space itself is not as still and empty as it seems. If you try to picture nothing, your mind might go to a simple image: an empty room, walls bare, no furniture, no dust motes in the light, just stillness, just absence, a place where nothing happens because there is nothing there to do, the happening. In classical physics, the vacuum was a bit like that imaginary room extended to infinity, space with all the matter taken out, perfectly silent and perfectly calm. No atoms, no light, no fields, just a smooth background, a zero you could safely write into the equations and then forget about. Quantum mechanics quietly ruin that picture. At the quantum level, even when you clear away every particle you can think of, you can't make the energy drop all the way to absolute zero. There is always a tiny leftover, what physicists call zero-point energy. The fields that fill space, especially the electromagnetic field, are never completely flat. They quiver, they fluctuate. Even in their lowest possible state, they have a faint, irreducible buzz. One way to imagine it is to think of a perfectly still pond. In classical thinking, if you stop throwing stones and let the wind die, the water can become a flawless mirror, absolutely flat. In quantum thinking, the pond never quite loses its wrinkles. The ripples don't vanish, they shrink, they soften, but there is always a tiny background tremble. Those ripples are like the vacuum fluctuations, brief, restless wiggles of energy that appear and fade, too fast and too small for our senses to catch. In the mathematics, this shows up as virtual particles, pairs of particle and antiparticle that flicker into being for a moment, borrow a bit of energy from the vacuum, and then annihilate one another, paying the energy back before reality notices the debt. They are not particles in the everyday sense. They're more like the grammar of the quantum field, ways the field can momentarily rearrange itself. All of that might sound poetic but suspiciously abstract until you learn that we can measure the influence of this not quite empty vacuum in the lab. Imagine two very flat, very clean metal plates facing each other, separated by a tiny gap, much smaller than the width of a human hair. Around them is as good a vacuum as experimentalists can manage. Air pumped out, stray particles minimized. By classical intuition, if there is nothing between the plates and nothing pushing on them from the outside more than from the inside, they should just sit there, unmoving. What actually happens is stranger. The plates are very gently pulled toward each other, as if an invisible hand is nudging them together. This is the Casimir effect. In the quantum picture, the space around the plates is filled with those jittery vacuum fluctuations, which you can think of as a sea of possible electromagnetic waves. But the gap between the plates is so narrow that only certain wavelengths fit between them, the way only certain guitar strings will vibrate at the right length. Outside the plates, all sorts of modes are allowed. Inside, the menu is more limited. That difference matters. Because there are fewer allowed fluctuations between the plates than outside, the pressure from the vacuum is ever so slightly lower in the gap than it is on the outer faces. The result is a tiny net push inward, a quiet squeeze from the restless fabric of empty space. The force is small but not imaginary. It has been measured, checked, and folded into the way we design delicate nanoscale devices. What began as a thought experiment about the vacuum ended up as a real effect that engineers must account for when they build things that operate at very small distances. So, the old picture of nothingness, a bare, silent stage, gives way to something more subtle. Even in the darkest, coldest, most evacuated region we can create, the quantum fields are still humming along in the background, like a distant engine you can't quite turn off. There is structure hiding in the emptiness. There is energy in what we used to call nothing. And to describe that humming more honestly, to make sense of particles, tunneling, and vacuum forces all at once, physicists had to shift their language, from talking about isolated little objects to talking about deep, ever-present fields that fill the whole universe. When physicists first started to realize that empty space wasn't truly empty, that it had this soft background hum of energy, it nudged them toward a bigger question. Maybe the universe wasn't really built out of tiny separate marbles at all. Maybe those marbles were just the ripples, and what really exists is the water they're rippling in. In the modern quantum picture, that water is a field. Instead of imagining a lone electron as a little speck flying through an otherwise empty void, you picture an electron field that fills all of space, everywhere, all the time. Most of the time, that field is calm, close to its quiet, lowest energy state. But when it's disturbed in just the right way, it produces a little localized bump of energy, a tiny knot in the field. That knot is what we call a particle. The same idea holds for light. There is a photon field spread through the universe. A photon is not a bead of light flying on its own through the dark. It's a pulse in that field, a packet where the field has briefly flared up above its resting level and then faded again. Every kind of particle we know corresponds to a different field: quarks, which live inside protons and neutrons, electrons and their heavier cousins, muons and tau. Neutrinos, so ghostly that trillions of them are passing through your body right now, without leaving a trace. Gluons, which glue quarks together. W and Z bosons, which handle a certain kind of radioactive decay. Photons. And the Higgs field, which quietly gives mass to many of the others, like a cosmic syrup that some particles wade through more heavily than others. Taken together, all of these fields and their excitations make up what physicists call the Standard Model. If you've ever seen the periodic table of the elements, the grid with hydrogen in the corner and gold, oxygen, iron, and so on, it's a catalog of the atoms that build chemistry and everyday matter. The Standard Model is like a deeper, more fundamental version of that table. It's a list of the basic ingredients from which atoms themselves are made, and the forces that allow those ingredients to interact. On one side of the Standard Model, you have the matter particles, 6 flavors of quark and 6 flavors of lepton. On the other side, you have the force carriers, the bosons, the photon for electromagnetism, gluons for the strong force, W and Z for the weak force, and the Higgs boson associated with the Higgs field. It's not the whole story of the universe. Gravity, dark matter, and dark energy sit outside this neat framework. But for everything from atoms to particle colliders, it performs with almost unnerving success. One of its gems is a theory called quantum electrodynamics, or QED for short. QED describes how the electron field and the photon field talk to each other, how charged particles emit and absorb light, how they scatter and interact. At first, people tried to write this down in straightforward equations and immediately ran into infinities, nonsensical answers that seemed to say the math was broken. It took years of careful work and a good deal of creativity to tame those infinities and reorganize the calculations so they gave finite, testable predictions. When they did, the precision turned out to be astonishing. Certain measurements, like the magnetic properties of the electron, match QED's predictions to something like 1 part in a trillion. It's as if you measured the distance from Earth to the Sun and got it right to within the thickness of a human hair. To keep track of what's happening in these interactions, physicists often draw little line drawings called Feynman diagrams. They look like simple doodles, wiggly lines for photons, straight lines for electrons and other matter particles, vertices where they meet, split, or rejoin. But each diagram corresponds to a specific term in the calculation, a specific way energy and momentum can flow through a process. Put together, they form a kind of picture language for the quantum world, a comic strip for fields exchanging quanta. If you zoom out, the overall picture feels a bit like a patchwork quilt. Different pieces of the Standard Model were stitched together over decades. Quantum descriptions of electrons and photons, then the strong nuclear force that holds atomic nuclei together, then the weak force that governs certain kinds of decay, and finally the Higgs mechanism to tie masses into the story. Each patch brought the theory closer to what we observe, until it became the framework that now underpins nearly all of high-energy physics. And yet, for all its rigor and all its impressive agreement with experiment, this entire construction is still about invisible fields quietly filling space, rippling in ways we can only infer from the traces they leave behind. The same vacuum that seems so still from far away turns out to be crowded with structure and possibility when you look closely enough. What's especially intriguing is that these quantum fields and the particles they produce aren't confined to distant laboratories or exotic accelerators. They're also the raw material of your own body, the atoms in your bones, the electrons flowing in your nerves, the photons that strike the cells in your eyes. The Standard Model isn't just a catalog of faraway things, it's the rule book for the matter that makes you up. With that in mind, it becomes a little less surprising and a lot more fascinating to hear that hints of quantum behavior may show up inside living systems themselves, whispering through the wings of birds, the leaves of plants, and the chemistry of scent. If you follow the quantum fields far enough, they begin to brush up against something very familiar: living things. Not in a sci-fi glowing DNA way, but in small, quiet hints that the strange rules of the microscopic world may have left their fingerprints on birds, leaves, and even the way we smell a summer evening. Imagine a migrating bird, no bigger than your hand, flying at night over an ocean it cannot see. Year after year, it leaves the same forest, crosses thousands of miles, and lands in almost the same patch of ground, guided not by road signs or city lights, but by the Earth's magnetic field itself. a field we cannot sense at all. Inside that small body, in the cells of its eyes, there may be a tiny chemical reaction that behaves like a compass. Two electrons become linked in an entangled state, their spins correlated in a way that depends on the direction of the magnetic field. As that field shifts, the probabilities of different reaction outcomes shift too, and the bird's visual system may turn those subtle differences into a faint pattern over the sky, a ghostly map laid on top of the stars. To us, it's just a bird turning slightly left instead of right. Underneath, it might be quantum entanglement nudging a pair of wings through the dark. Now, picture a leaf held up to the sunlight. From far away, it's just a flat green shape. But if you could shrink yourself down and walk along the interior of that leaf, you'd find a maze of tiny structures catching photons and passing their energy inward, like a series of little handoffs in a relay race. Classically, you might imagine that energy wandering around randomly, bouncing from molecule to molecule until it happens to find the right place to be used. Yet plants are astonishingly efficient at this job, far more than you'd expect from a simple random walk. Some researchers think that, for a fleeting moment, the captured energy isn't just in one path or another. It spreads out in a quantum superposition across many routes at once, like a soft glow smeared over the network. Instead of checking each corridor one by one, the excitation explores many possibilities together, and constructive interference gently pushes it toward the most efficient path. The whole dance happens in trillionths of a second, and then the strangeness fades, leaving only the steady, familiar fact that sunlight has become sugar in a leaf. Even our sense of smell may have a quiet quantum ingredient. We often imagine that we recognize scents the way a lock recognizes keys. A molecule with the right shape fits into a receptor in the nose, and the brain labels it rose or coffee or rain on hot pavement. Shape does matter, but there are hints that it might not be the whole story. One proposal suggests that when a scent molecule binds to its receptor, it allows an electron to tunnel within that receptor, slipping through an energy barrier it couldn't cross by classical rules. Whether that tunneling happens, and how easily, can depend on the molecule's vibrational frequency, the tiny quantized ways it can jiggle. In that view, the nose isn't just feeling for shapes. It's also, in a way, listening for very small, very fast quantum notes. None of these ideas are settled. Quantum biology is a young, cautious field, and scientists are still arguing, testing, refining. But taken together, these stories whisper that quantum behavior doesn't stop at the edge of a vacuum chamber or a particle collider. It may linger briefly inside warm, messy, breathing systems, influencing wings and leaves and memories of a favorite perfume. And that raises a gentle question. If traces of quantum weirdness can survive inside something as fragile and complicated as life, why doesn't the everyday world around us look more like a double-slit experiment left running all the time? If quantum strangeness can show up inside the eye of a bird or the heart of a leaf, it's natural to wonder why your coffee mug on the nightstand behaves so politely. It never seems to be in two places at once. It just sits there, solid and certain, waiting for you in the morning. The bridge between those worlds has a name: decoherence. You can picture it as what happens when a delicate quantum maybe is exposed to too many curious neighbors. A particle, left alone, can be described by a smooth wave function, a spread-out cloud of possibilities, interfering with itself the way ripples on a pond overlap and create patterns. But nothing in our everyday world is truly left alone. Every atom in that coffee mug, in your pillow, in your own body, is constantly brushing up against countless air molecules, photons of light, and vibrations in the surrounding matter. Each of those tiny interactions is like the environment taking a little peek, not by conscious observation, but simply by becoming entangled with the system. As those entanglements pile up, the original tidy quantum superposition gets shredded into a huge tangle of correlations between the system and everything around it. The interference patterns that once defined the both-at-once state get washed out, Not because the wave function has literally disappeared, but because all the different branches are now tied to different, inaccessible states of the environment. From your perspective, the shimmering cloud of possibilities has hardened into one ordinary outcome. The mug is here, not there. Decoherence doesn't answer every philosophical question about measurement, but it explains why we don't see cats halfway between alive and dead, or coins hovering between heads and tails on our kitchen tables. The quantum fuzz is still there in principle, but it has spread into so many degrees of freedom that we can no longer make it interfere with itself. The world you move through feels stable because the environment is constantly, relentlessly recording which branch you're on. And yet, even when decoherence is taken seriously, quantum experiments still find ways to unsettle our sense of time and causality. Some of the most disorienting are the so-called delayed choice and quantum eraser setups, which are really just clever twists on the double-slit idea. Imagine, again, photons passing through a pair of slits on their way to a screen. If no information about which slit each photon took is available anywhere, you get the familiar interference pattern, as though each photon explored both paths at once. If you arrange your experiment so that which path information is unavoidably recorded, even if no human ever looks at it, the interference disappears and the pattern looks like simple particles taking one route or the other. Now here's the unsettling twist. You can design things so that the decision to keep or erase the which path information is made only after the photon has already passed the slits. When you later sort the data into groups, those where the path information was preserved and those where it was effectively erased, the interference pattern returns in the erased subset and vanishes in the other. It feels at first glance as though a choice made in the present has reached back and rewritten what the photon did in the past. Physicists are careful to point out that no real message is being sent backward in time. What changes is not the old history, but how the correlations between particles and detectors line up once you take all the data into account. Still, these experiments force us to admit that our usual story, first events happen, then we measure them in a simple, linear order, is not quite how quantum processes organize themselves. In this view, information takes center stage. Whether a system behaves like a spread-out wave or a localized particle depends not just on what really happened, but in whether the universe has, in any sense, kept a record of the possibilities. When that record is fragile or erasable, interference can survive. When it's robust and scattered into the environment, decoherence locks in a definite outcome. And once an outcome is locked in, we meet another, quieter puzzle. Each single result, each click on a detector or dot on a screen, seems to arrive without any deeper cause we can uncover. Only a probability that it would show up there instead of somewhere else. As you drift further into the night, you might find yourself wondering, is that unpredictability just a reflection of our ignorance? Or is there a genuine, irreducible randomness beating at the heart of the universe itself? Physicists have spent decades trying to make sense of that uneasy question. Is the universe rolling loaded dice we can't see? Or are some events truly without any deeper cause we could ever uncover? When they look at certain quantum experiments, the answer that keeps coming back is strangely humbling. Take a radioactive atom, for example. You could gather an enormous crowd of identical atoms and watch how quickly, on average, they decay. The statistics are beautifully precise. You can say that after a certain amount of time, half of them will have transformed, and after another equal stretch, half of the remaining ones will go too. That regularity is so reliable that we build clocks and scanners and medical treatments around it. But if you focus on just one atom, the story changes. There is no hidden stopwatch ticking away inside it that we can measure. There is no extra variable we can poke that tells us, this one will decay at 2 minutes, that one at 7. All quantum theory offers in the end is a probability distribution, a quiet rule for how often each possible outcome will appear in the long run, and then, for each individual event, a kind of disciplined unpredictability. It's as if the universe refuses to script every single moment in advance. but still insists on following a larger pattern. The randomness is not wild or chaotic in the way a broken machine might be. It is closer to a soft, statistical rhythm, where each click on a detector is unpredictable, yet the overall melody of many clicks can be forecast with astonishing accuracy. That tension between the unpredictable and the reliable isn't just a curiosity for laboratories. You live inside something very much like it all the time. Think about waiting for the results of a medical test. On paper, the doctors can tell you the odds. They know from thousands of cases how often a particular outcome shows up. But for you, lying awake in the dark, there is only one result that will eventually arrive in your own life. Until it does, your mind drifts between futures. One where things are okay, one where you have to adapt to something harder. Or imagine sending off a job application, or a manuscript, or a message you're not sure the other person will answer. Statistically, you might have some sense of the chances, but emotionally, you're in a kind of superposition. Hope and worry, excitement and doubt, all present at once. No amount of refreshing your email will let you measure the outcome before it's time. In that sense, quantum randomness can feel oddly familiar. We are constantly making peace with events we cannot control, living in that interval before the coin lands, before the phone rings, before the doctor walks back into the room. We move through a world where some things are stable and law-like, yet many of the moments that shape us arrive with no warning. There's a temptation, especially when we're anxious, to believe that if we just knew enough, if we just had the right data, the right insight, the right ritual, we could tame all of that uncertainty. Quantum physics quietly suggests that this dream has limits. Even in a theory that predicts so much, there may be randomness woven into reality itself, not as a flaw, but as part of how the universe breathes. Seen in that light, not knowing everything stops being a personal failure. It becomes a basic condition of existing in this kind of cosmos. You are not the only one who has to live with incomplete information. Every particle, every atom, every star evolves in a landscape where only probabilities can be laid down ahead of time. So as you lie there, somewhere between awake and asleep, with your own unanswered questions hovering around you, you might give yourself permission to rest inside that uncertainty instead of fighting it. You don't have to solve every mystery before you close your eyes. You don't have to predict every outcome to be allowed a few hours of peace. The same universe that leaves room for randomness also allows for patterns, for meaning, for small acts of kindness and quiet evenings like this one. You are carried by that balance whether you think about it or not. And as the ideas of quantum chance grow softer and more distant, you can let them blur into the background, making space for a simpler, more human thought. That it's okay not to know how tomorrow will unfold, and it's okay to sleep anyway. Somewhere along the way tonight, the sharp edges of these ideas have probably started to soften. The words wave function, superposition, entanglement, and decoherence have blurred together a little, the way distant city lights smear into streaks when you half close your eyes. That's perfectly fine. This was never meant to be an exam. It was an evening spent wandering through a very small, very strange corner of the universe. Slowly enough that you could fall asleep in the middle of the tour and not miss a thing that truly matters. You might still have a few images floating around. A quantum coin that doesn't pick heads or tails until you look. A cat in a sealed box that exists in an uneasy maybe. A ghostly cloud around an atom where an electron might be hiding. Maybe you see a migratory bird quietly feeling its way along Earth's magnetic field, or a leaf using quantum tricks to guide sunlight toward the work of life. Maybe you picture empty space, not as a perfect silence, but as a room with a faint, restless hum beneath everything. If the details feel out of reach, that's all right. Your brain is allowed to let go now. You don't have to keep track of every experiment or every paradox. It's enough to carry a gentler thought. That reality is richer and more mysterious than the everyday story we tell ourselves, and that you, breathing slowly in the dark, are woven into that mystery just as surely as any particle or star. Earlier tonight, I asked where you were listening from. A bed, a long train ride, a quiet chair by a window. Maybe you answered in the comments, or maybe you just answered silently in your head. Wherever you are now, that place has become part of this little ritual, your own corner of the universe, your own patch of space-time, where curiosity and rest are allowed to share the same space. There's a good chance you drifted off for a moment, somewhere back at the double slit, or with the cat, or with those two metal plates whispering to the vacuum. Maybe you woke up again and rejoined the story halfway through. That's not a problem. In fact, that's the design. These journeys are meant to be soft enough that sleep can slip in between the sentences without needing permission. As you lie there now, you don't have to decide whether the universe is truly random or secretly ordered. You don't have to choose a favorite interpretation or decide exactly when a wave of possibilities becomes a single outcome. You can let those questions float like distant lanterns on a river, slowly drifting away downstream, growing smaller and dimmer until they are just a comfortable glow on the horizon of your thoughts. What you can keep, if you like, is a quieter reassurance that not knowing everything is allowed, that being a small, finite person in a vast, complicated cosmos is not a failure, but a kind of beauty, and that there is room inside all this strangeness for simple things like a warm blanket, a steady heartbeat, and a night of deep sleep. If your eyes are still open, you're welcome to close them whenever you're ready. Let your shoulders sink a little deeper into whatever is holding you up. Notice the rhythm of your breathing smoothing out, the way your thoughts lengthen and slow, the way the day begins to loosen its grip. From the Quantum Slumber, thank you for spending your night with the quiet side of the cosmos. Wherever you're listening from, whatever time glows on the clock beside you, you're not alone in the dark. Sleep well, rest kindly, and good night.